My dear friends, welcome to Rajashekar classes on Applied Data Science with Python. This is lecture number 240, that is 240. In this lecture, we will try to understand geometrical interpretation of SNE. Before understanding this geometric interpretation, let me recall what I discussed in my previous lecture, that is in lecture number 239. SNE is considered as as state of the art in the area of dimensionality reduction. In the area of dimensionality reduction. This is first point which I discussed in my previous lecture, specifically for visualization of very high dimensional data. Although there are many techniques available to reduce high dimensional data, for example PCA, this one we discussed for dimensionality reduction. SNE considers, you can say SNE considered one of the best technique. I can say it is one of the best technique available for dimensionality reduction. I can say it is new area of research. As I discussed in my previous lecture, this work is published in the year 2008. The way PCA works is that it tries to maximize. Before discussing about SNE, let me recall few things about PCA. Let me say like this: the way PCA works is that it tries to maximize the variance towards, let me write like this, it tries to maximize the variance. This is about PCA, isn't it? Maximize the variance towards the principal components. That's what core idea behind your principal component analysis. It tries to maximize the variance towards the principal components and the other components in the sense having low variance. Other components means what? Let me write. And other components. What is the meaning of other components? Other components means having low variance. Having low variance are declared as, these are declared as noise points. This is the biggest drawback with our principal component analysis. So PCA tries to maintain global structure. This also I discussed. Global structure. It will try to maintain global structure of the data. It tries to maintain global structure of the data. Just if you observe this particular figure, we have two features. What are this one? Feature 1 and feature 2. We have two features, F1 and F2. Along with, you can see that there are two clusters, just the cluster A and cluster B. In both sides, I will repeat, we have two features, F1 and F2, along with you can see that there are two clusters, that is cluster A and cluster B, two clusters of points in both sides of the principal component 1. Just see, above the principal component 1 we have one cluster, and below the principal component 1 we have another cluster. So if you try to reduce two dimensions, if you try to reduce two dimensions into one dimension, isn't it? If you try to reduce two dimensions into one dimension, PCA will maximize the variance. PCA will maximize the variance, isn't it? Will maximize the variance and will get the principal component 1. This is, will get the principal component 1 as the final feature. This you must understand. As it has got maximum variance, this will be the final feature. I can say this is final feature. The data points of the clusters will project on the principal component 1. Means all these data points will be projected on to principal component 1, isn't it? In similar manner, these points will be projected, these points will be projected, these points will be projected. This I already discussed. These points will be projected like this. In this region, what happens? In 2D, they are well separated, this cluster and this cluster. But whereas, while converting 2D to 1D, what's happening? You are losing information. Why? Because all these points are superimposed here. You cannot separate them, isn't it? The data points of the clusters will projected on the principal component 1 and will superimpose on each other. So we will lose information. We will lose cluster 1, as you cannot, as cluster 1, cluster A points and cluster B points are projected in the same region. You cannot separate them. We are losing the information. That is the one of the drawback of PCA, which I discussed many times. As it is important, I am repeating this again and again. SNE. Now, till now we were saying something about PCA. What about my new research area, SNE? SNE, unlike PCA, I can say SNE, unlike PCA, preserves, unlike PCA, preserves the local structure, preserves the local structure, preserves the local structure also, isn't it? Local structure also, local structure of the points, it can preserve that local structure, whereas it is not possible with PCA. How SNE works geometrically. Now we will try to understand real geometric interpretation of today's topic, that is SNE. As it is mentioned that SNE preserves, I will write SNE, as I have mentioned, SNE preserves. It preserves. What will it preserve? SNE preserves local structures. Local structures. This particular slide picture I collected from medium.com website. Let me repeat it. SNE preserves the local structures of data. Local structures of data while converting from higher dimension to lower dimensions. In this case, if you convert data from 2D to 1D, here in this context 2D is higher dimensional, 1D is lower dimension, it can preserve, SNE can preserve local structure of the data. I will repeat, as SNE preserves local structures of the data while converting from higher dimensions to lower dimensions. That's the point where the terms neighborhood and embedding are useful. This now we will try to understand what is this neighborhood and embedding. In this particular image, just see this particular picture, what it says, we can see there are three clusters. Let's see, this is cluster 1, cluster 2, cluster 3, isn't it? There are three clusters in higher dimensional space. In this context, what is higher dimensional space? 2D space is higher dimensional space. We are calling them clusters. Your cluster 1, cluster 2, cluster 3. I can say these are neighboring points. This point is neighbor to this point. This point is all in cluster 1 they are neighbor to each other. In clusters 2 these points are neighbors to each other. In cluster 3 these points are neighbors to each other. That's neighboring. Geometrically they are very close, but this point cannot be neighbor to this point. They are very geometrically they are far away. This point cannot be neighbor of this point. That's the meaning of cluster. That's the meaning of neighbor. Neighbor means geometrically they must be very close. I will spend a lot of time how it works in future classes. What Disney does while reducing to lower dimensions, one dimensional in this case, means what Disney does while reducing from 2D to 1D or from higher dimensional to lower dimensional, what Disney does while reducing to lower dimensional, in this case 1D, is that it embeds the points onto lower. I will write this point. Disney embeds the points, embeds the points onto lower dimension, while preserving the distances, like higher dimensional points, higher dimensional points. What does it mean? It embeds the points. It embeds the points onto lower dimensions while preserving the distance like higher dimensional points. Higher dimensional points means in this case that is 2-dimensional points. Here higher dimensional is 2 dimension, lower dimension is single 1 dimension. I can say points are I will repeat. It embeds the points onto lower dimensional while preserving the distance like higher dimensional points are projected. Higher dimensional points are projected to the lower dimensional points, but the intra-cluster distances are similar. Intra-cluster distances. I can say like this: intra-cluster distances are similar. This point is important. Intra-cluster distances are similar, but Disney does not promise to preserve the inter-cluster distances. Intercluster distances. This is important. Yes, Disney preserves intra-cluster distances, but Disney need not preserve inter-cluster distances. That is, in high dimensions. In this context, high dimensions means 2D. The red cluster, for example, this is my, let me say this is my cluster 1, this is my cluster 2, this is my cluster 3. In cluster 1, all these are neighboring points. In cluster 3, all these are neighboring points. In cluster 2, all these are neighboring points. This is 2D. I am converting into 1D. If you convert these, as I told you, Disney preserves inter-cluster. Disney preserves intra-cluster. As I told you, intra-cluster distances this can be preserved, isn't it? It will be preserved, but we are not sure about intercluster. What does it mean? I will repeat. Intra-cluster distances are similar means if you see this distance between this is the data in 2D. This is the data in 2D. This is the data in 1D. First we must realize that. I am embedding these neighboring points I am embedding into one dimensional space. If I say this is x1, this is x2, this distance in 2 dimension is same as this distance in 1D. Isn't it? In similar manner, if this is one point, this is another point, this distance here also it will be same. Means distance in 2 dimensional, distance between these 2 points is similar to the distance between the 2 points in 1D. Means if I say something like this, let me say like this, let me say this is x1, let me say this is x2. Yes, this x1 is transformed here x1 dash. This x2, let me say this is transformed into x2 dash. What does it mean? Distance between x1 and x2 is equal to distance between x1 dash comma x2 dash. That's the idea, isn't it? For example, if I say this is some x4 and this is x5, after projecting they will be transformed into x4 dash comma x5 dash. What does it mean? Distance between x4 x5 is equal to distance between x4 dash and x5 dash. That's what it says. That intra-cluster distances are similar, but we are not sure about inter-cluster distances. For example, just see, this cluster 1 points are projected here, cluster 2 points are projected here, cluster 3 points are projected here. If you speak strictly, cluster 1 and cluster 3 are close to each other in 2D. In 2D they are close to each other. While converting into 1 dimensional, your cluster 1 is here, your cluster 3 is here. They are not having same distance. That's what it says. I am repeating, intra-cluster distances are similar, but SNE does not promise to preserve inter-cluster distances. That is, in higher dimensions, in this context higher means 2D. In our higher dimensions, this is 2D, that is higher dimension. The red cluster is close to blue cluster, but in the lower dimension, that is in 1D means here, these clusters are quite far. Just see, these clusters are quite far. This is the concept of neighborhood embedding. This is known, you are embedding 2-dimensional points into 1-dimensional. This is known as embedding. You know what is neighbors. All the points which are in the same cluster are neighbors to each other. The above process discussed has a highly mathematical base to solve. This, if you want to do all these things, you must need highly mathematical base. You must have clear-cut idea of high mathematics, especially topics like optimization. I will spend a lot of time on optimization in future classes. In layman's term, SNE uses symmetric probability density function. SNE uses symmetric I already discussed probability density functions in my previous classes. It uses probability density function. In both higher and lower dimensions. Here also it uses probability density function. In lower dimensions also it uses probability density function to preserve the neighborhood. Although due to the curse of dimensionality, the points in the higher dimensional space tends to get crowded in lower dimensional space, causing the crowding problem. Here we have one difficulty, that is crowding problem. I will discuss this in my next class. What is crowding problem? The crowding problem, SNE uses, I will repeat, SNE uses students T distribution. Again, how T distribution solves the problem has rigorous mathematics behind it. but T distribution promises that it will try best to preserve the neighborhood by means of probability. Probability means I can say it is stochasticity. That's why it is T distributed stochastic neighborhood embedding. I will continue my discussion on this SNE in my next few lectures. Time being, just try to understand try to understand basic drawback with PCA and how Disney can resolve it, and try to understand geometrical interpretation of geometrical interpretation of embedding, so that if you have any difficulty, just please keep a comment. Thank you very much.